Hello, community. Last time we were talking about Azure Cognitive Search in combination with the Azure OpenAI set with GPT-4. And today I want to show you an alternative to this. So remember last time we left off, we had here our GPT-4 system. We had here from OpenAI a second model, the text embedding model, the ADA 002 model. We had here the typical retrieval plugin from OpenAI with the API endpoints from Upsert and Query. I showed you how they are in the dynamic flow. And we have here, and we looked at the example of Azure, here our Postgres, free open source relational database management system with the PyG vector edition, so we can calculate here our cosine similarity for a semantic search. If you have a prompt and you ask GPT-4 a question where it needs external data that are not within the GPT-4 pre-trained data system. And we have said, okay, these are our external documents. If you're a company, these are your corporate secret documents, and you want to use them in combination with GPT-4. This is where we left off. So today we have a new motto, and it is, let us save some money. Why you want to give everything to Microsoft and OpenAI? Can we have an update to the system? So let's have a look. I want to focus today on the text embedding. Oops, wrong. And it is not only the embedding machine, like I told you last time, but before this we have a tokenizer. And OpenAI uses here a specific tokenizer. So we have a tokenizer, and then we have the embedder. And as a third step, I want that you remember cosine similarity. So remember, watch out for 3 steps: tokenizer, embedder, similarity calculation. This is exactly the functionality here of our second OpenAI model, of the plugin, and of our Postgres. As I told you last time, if you want to optimize for domain-specific data, you can either go here with OpenAI's text embedding ADA system, that is everything on every topic on the complete internet for everybody. You have news, politics, finance, style, beauty, whatever. And I give you last time the example, I'm interested in physics. And I want to build something where all of the embedder is only focused on one domain with a very high resolution. This is really here what I'm looking for to work for my company. Embedding machine, and I told you, yeah, we have to do the tokenization first. So let's have a look how we can do this. So how do we start with our own tokenizer? Yeah, it is easy. If you know that there is an open sourced tokenizer somewhere in a repo, well, that has been optimized for, I don't know, the financial domain, or medical study, medical research, or biochemistry, or whatever domain you're interested in. There are tokenizers available free of charge, open sourced. Go grab one, try it out, go with it. Or if you're really an expert, hey, we're gonna build our own tokenizer. And this tokenizer will be the best optimization you can get, because we work only on your specific domain knowledge, nothing else. So I give you an example. These are here my documents. This is a body of documents of 100 scientific preprints on the topic of quantum field theory in particle physics. All of the publications of the last 2 years. Maybe it's 2000 scientific publication, never mind. In this publication, those are my words that I work with. Quantum field dynamics, quantum chromodynamics, perturbation theory. There's nothing about US politics in there. Those are my words, my sentences, with their special semantic meaning. This means when I will apply an AI system, a self-attention mechanism, on each word in the sentence, I will get a very high resolution. So a resolution that an ADA embedder, can never achieve. This is why we do this. So I tell my tokenizer, if it would be an AI already, hey, listen, tokenizer, you learn your tokens from this set of documents. You optimize yourself, your token specification for this domain-specific training dataset, but only this. And you generate your tokens based on these documents. So I can be sure that all the tokens here that come out of my special tokenizers are tokens optimized for particle physics. Maybe you want to go for legal matters, or you want to go for medical or biochemistry. You choose your domain. Great. So I say now you have your tokens optimized for your domains. And you have chosen a specific tokenizer type. Let's say you go with byte per encoding. Every tokenizer type has a special optimization criteria. Inform yourself. If you want to see, for example, instead of byte per encoding the BERT tokenizer, I have this video for you. If you want to have a little overview over the tokenization in general for a domain-specific knowledge here with a byte per encoder tokenizer, I have here this video Expert 49 for you. Yes, I have more than 50 videos on this. Next up, now that we have our tokens, what we have to do? Now we have to come to the vector representation of our tokens. Let's say a token is just the word. Let's say one token is the word electron. What is the semantic vector embedding of a word electron? Therefore, we have to build a vector space where all tokens live and where I calculate their semantic closeness to each other. This is all there is on this slide. So we activate here a machine, we call it an encoder stack of the transformer architecture, or maybe you're familiar with the BERT model, and embed here our chosen sequence of words. For me, I work with sentences. If you have huge amounts of documents, maybe you go with the sequence of paragraphs of text. It depends on your specific task. I built now a new vector space. I mean, BERT runs for 10 hours and builds a new vector space. Given now a new distribution of the tokens in the semantic clusters based on the sentence information in my training dataset. So SBERT, sentence BERT, the sentence transformer architecture, will calculate now the semantic vector representation of the embedded objects. So I have here a vector representation of my tokens. Tokens are either you go with words, you go with sentences, whatever you have, I go with SBERT sentences, and I choose the semantic relationship between the words in a sentence to have here then a vector representation of sentences. Beautiful. Oh yeah, 2 videos for you. If you prefer PyTorch, here, this video SBERT 51 shows you how to train here SBERT on PyTorch. And if you prefer here the TensorFlow 2 and the Keras framework, the Keras API, a very beautiful, powerful API structure, here is TensorFlow 2. The same topic, just one time PyTorch, one time in TensorFlow. And after we have done this is our third step, and this is our last step. Now that we have a pre-trained SBERT system, we code now a semantic information retrieval system. And we call this neural search. In this video, SBERT 42, code semantic information retrieval system with SBERT sentence transformers. Now again, in PyTorch, whatever you like. Go with whatever language you prefer. Beautiful. So what have we achieved? Let me show you this in comparison. In my last video, I showed you here GPT-4 with another OpenAI model with the official OpenAI retrieval plugin that works here with our beautiful API endpoints to insert new documents into this, get a tokenization, get a vector representation of the query term, have the query API endpoint, and then calculate here the cosine similarity from an external knowledge database, Postgres, that is external to GPT-4. Beautiful. So all of this here that you see, if we take all of this, what we achieved with all of this, here's it. We had here, this is now the developer platform of Azure, OpenAI, plus the cognitive search return. So this is more or less the result that we get. So we have here, for example, a question. And to answer this question, GPT-4 now takes some external enterprise data to GPT-4 and says, hey, listen, in this file, this paragraph contains the answer to this question. And I've even found another document in the corporate database. Here is another paragraph from another document that might also contain the answer. And normally, as I told you in my last video, default is you get 3 information blocks back. So all we achieved with our plugin, with our external vector database, our external vector store, our whatever you want to call it, cognitive search from Azure, we got now to answer a simple GPT-4 prompt. We now return a relevant solution here that we can add to the prompt when we input here our question to GPT-4, and we provide GPT-4 with some external knowledge. Result, additional sentences for our prompt. Beautiful. Now, if I take all of this and I say, okay, if we want to substitute all of this and we want to upgrade it from a database structure, and it isn't a semi-intelligent database structure, don't get me wrong, it's great what they did. But if you want to upgrade it to an AI system, oh yeah, we have a sentence transformer system in PyTorch that is an information retrieval system. So let's look at this. We have some external documents or corporate documents. And first step is we have a tokenization of all our base documents. So we find the perfect tokenizer. Second step is all these tokens, we have now an embedder if you want. We find in a vector space that we calculated within Expert, we find here, if we go, the objects are sentences. We have now all the sentences that go together on a specific topic. We have a topic cluster generated in this vector space. And the embedder gives us the vector coordinates of our single objects, and our single objects are sentences. And in those sentences, we have words where the relation of the word in each sentence to another word in the same sentence is calculated by self-attention. So what we do now, the last one is, if I have a query here, tell me about physics. I have now to find physics, the answer to physics here with a mathematical operation that is called the cosine similarity in the easiest case. So what I created here in my Expert system is I have a tokenizer, I have an embedder, and I have a similarity. And if you remember at the very beginning of this video, I told you watch out for these 3 terms. And now we have here the same terms, but in an updated AI system. So we have a domain-specific AI system for information retrieval, or IR, given that we have here a query, a prompt, a question that I ask GPT-4, and GPT-4 needs additional, maybe real-time information from external data sources. Could be text, could be SQL, could be whatever. So you see, this is an alternative to save your money. You can build this yourself in your own company, because the real intelligence, the real beauty is GPT-4. But for the tokenization and the embedder and the cosine similarity, if you are focused on one domain, you do not have to rely on third-party solutions that are really, really expensive. Okay, so what I get with this solution now, exactly the same. I have here a question that goes into GPT-4. GPT-4 needs additional data, and I get here the sentences back from my cosine similarity. Remember here, my cosine similarity gives me 3 results back, 3 sentences or 3 paragraphs of text that contain the solution to my query, physics. Yes, physics can be included with physics you should use for. So those text answers go back here for my more information added query and then go into GPT-4. When I achieved exactly the same thing now with this one. So you see, those systems are equivalent. Only the last one is even an AI system and has some inherent intelligence. And you know, the funny part is, if you think about this, let us revisit the system architecture we put together here. You remember the classical transformer, the model architecture as patented by Google? We have here our encoder stack, and we have here on the right-hand side our decoder stack. And you know that GPT-4 is an autoregressive model that is built here on, apart from other elements, on the decoder stack of a transform. This is our GPT-4. And you never guess what SBERT is. SBERT is exactly the encoder stack of our transformer. So you see, if you combine now those two systems, it is interesting that together, again, they form a complete transformer architecture. This is it for this video. I hope it was informative and hope to see you in my next one.